I need a chair that swivels like yours.
Oh, sorry. Makes it maybe a little bit seasick. I'm waiting to see my chat box.
You're so minimized, they're not even gonna notice you swiveling this. Like try to look for you.
Mhm.
All right.
Hey, everybody. Welcome to our very first lesson for AB Calculus. And this lesson is 7.1, Modeling Situations with Differential Equations. So just let me introduce myself first. My name is Verge Cornelius. I teach at Lafayette High School in Oxford, Mississippi, and I've been teaching for 30 years. I also teach Algebra 1. I have a lot of great colleagues, both at Lafayette and all over the world, all over the country. And one of them is one of my team teachers right now. Here he is.
Hi, I'm Mark Corrali. I teach at Ryan High School in Denton, Texas, and I also have been at this nearly for 30 years. Verge and I are actually good friends, so hopefully that'll come across in these videos. And we're here for you guys.
So just a little bit about why we're here. We're here because College Board contacted us last week and asked if we would be interested in doing some virtual lessons to help students finish the course for AP Calculus and also help them get ready to review for the AP exam. And I anyway, I just said sure, and I didn't even think about it, and here we are. What we're going to do is we're going to finish off the material for AP Calculus, one lesson at a time. And then we are going to, one day at a time, get ready for our AP exam. I do want to say a special welcome. That's okay. I do want to say a special welcome to all of the students right now who are joining us, especially those of you who don't have much contact with your teacher right now. Mark and I are both teachers, and we know that different schools are handling this in different ways. Some folks have a lot of contact with their teachers right now and maybe have way too much work to do. And then others of us have no contact with our teacher, and those students were able to seek out these videos anyway. And so that's wonderful. Also, huge welcome to our teachers who are out there listening to us, watching us, and also a huge welcome to our colleagues who are watching us and supporting us. And we love you all very, very much. All right, Mark, you can do the next slide.
All right.
All right. So the next few weeks, just as an overview before we get into our lesson today, because I know this has been a lot of people's concern and questioning and things like that. We are going to pick up where a lot of students left off and teach Unit 7, which is differential equations. And we're going to start that today. And that's going to take us about 6 lessons to teach that. Then in Unit 8, we are going to do selected topics of applications of integrals as they tie back to previous units. And you'll see what we mean by that. Many of you know exam units 1 through 7 for AB, but Unit 8 has so many great topics that tie back to things that are going to be tested. And so we definitely want to instruct on those topics. And then we are definitely towards the latter part and moving up towards May. We're going to review all tested topics and also give you lots of test taking strategies for the exam. And I know that there's lots and lots of questions out there about the exam. Guess what? We have questions too. We don't know anything. We're not going to know anything until April 3rd. And that's when we're waiting.
We're waiting for April 3rd, just like everyone else.
Yeah, we really are. So we will, as soon as we know more, we will start weaving that into our daily lessons with you. But the most important thing is to do some calculus. So that's what we're going to go ahead and do. Anything else, Mark, before we get into our warm up?
I think we're pretty good.
Okay, so let's go ahead and look at our schedule for the day as opposed to the overview of the next several weeks. We did our introductions. We're going to go ahead and do a warm up in your classroom. That might be called a do now or maybe a bell ringer. And that takes about 5 minutes. And then we're going to do our lesson 7.1, modeling situations with differential equations. And that'll be about 15 minutes. We're going to be very careful to try and keep this lesson to 45 minutes. We'll do guided practice for 10 minutes, but we're going to kind of alternate that as we're teaching. So it'll kind of go back and forth. I might do a few examples, then I'll have you try and do one. That makes me think to myself, you should have a pencil right now, and you should have a notebook right now, so that you can be taking notes like you're in class. If you're watching live right now, if you can't pause, I had a conversation with a current student earlier today, and she was trying to watch an AP Live this morning, and she lives pretty far out in the country, and she said, I couldn't watch it live very well, so I'm going to watch it later tonight, and it'll be good because I can pause it as I watch it later tonight too. So that's definitely an option, is that you might want to watch it later and then pause so you can jot stuff down. Then towards the end, wrap up and further resources. This is something that Mark and I have really worked hard to provide teachers and students with resources. Everything that we do in our lessons, we will have a PDF of it in the little bit.ly down below. And we'll talk more about that towards the end. And you can always go to that Dropbox. The bit.ly link will take you to the Dropbox.
Yeah, it should be in the description for the video and the channel.
Yes, it'll be in the description. That's right, Mark, for the video and the channel. So anyway, we'll talk about that a little bit more at the end. Okay, let's go ahead to do the most important thing, and that's the math part. And so here's our warm up. This is what I call a warm up in my classroom. And the directions are: model the following situation with an equation. And the situation is the area of a circle is proportional to the square of its radius. All right, how does that look? Did I do it, Mark?
Looks good to me.
Okay, all right. So what I just did just now, and is I booted Mark off of the PowerPoint, and now I'm here on just my little, hover cam. I actually don't honestly teach off of a hover cam normally. True confessions, I'm up at the board, or I'm walking around watching my students work, but this is a little different. All right, so here's our warm up. And I'm trying to model this situation. The area of a circle is proportional to the square of its radius with an equation. I'm taking a verbal description, and I'm going to go ahead and write it as an equation. This is something that you probably would have done, last year, year before, definitely before calculus. There's no calculus in this little warm up right here. So let's see, what would I do? The area of a circle, well, as a mathematician, I have to kind of assign that a variable. So I might say, I'm going to call that A is, there's my equals, is proportional to the square of its radius. Okay, so proportional means that there's some constant of proportionality. I'm going to call it K. It could be C, it could be something else, multiplied by the square of its radius. So R squared. So that would be the situation modeled with an equation. A is equal to K R squared. Now, of course, we all know that this K is equal to what? Mark?
In the rehearsal, I said half of tau, but I guess we'll go with pi day.
Okay, so either half of tau or pi. Okay, so we know that this K is equal to pi, but in any case, there's our equation. So now to get into really what we're doing in terms of calculus here, this is very high tech, I know. I'm just, wow. All right.
That font looks like handwriting.
That looks like it's my font, Mark. You know that. We worked on that over
amazing.
My own font. Okay, modeling situations with differential equations. I ran out of room as I was writing that. DE is how any mathematician is going to refer to differential equations, except for people who call them diffie-Qs, which is also another abbreviation. So modeling situations with differential equations, our entire unit is about differential equations, but we're going to model situations in this one section. So here's my first example. The rate of change of A with respect to T is proportional to R. It sounds a lot like my warm-up, doesn't it? It's got a little bit of difference though. The rate of change of A with respect to T, that's my differential expression. The rate of change of A with respect to T, dA, dt. Now, if you think back to implicit differentiation or related rates, you saw expressions of the derivative written in this form. A lot of times we'll write a derivative with just an f prime or a y prime, but this with showing the differentials like that, that's what we're going to be translating today. There's my equals. I already wrote it here. Proportional to R. So K, my constant of proportionality, times R. Translating from English, a very cumbersome language, to math, clean, tight, economical. Second example. The rate of change of Y with respect to X is proportional to Y. Let's see about translating this sentence into a differential equation. The rate of change of Y with respect to X, that's dy dx, equals proportional to Y. So I'm going to have a constant of proportionality. There's my equal sign. And it doesn't have to be K like before. It doesn't have to be K every time. It could be any letter. Variables can be arbitrary. It could be C this time. So the rate of change of Y with respect to X is proportional to Y. dy dx equals C times Y. Now, the next set of examples we're going to do comes from an activity that was really just written very, very recently. And I'm going to go ahead and move this so that it's easier to see. But this is what's going to be in our Dropbox. And it's a quiz trade activity that was written by Vicki Carter, who is a fabulous math teacher in Florence, South Carolina. We love her very much. We know her very well. And we want to share this activity with you. And also, she, of course, gave us permission to do it. I think it was about 7 a.m. on Saturday morning when we were talking on the phone, getting permission. She said, of course, you can do it. So all of these are going to be available in that Dropbox. There's no need to scramble and try and write them all down now, but you can make a note of the number and then go back and write them for yourself. All right, so the first one is the rate of change of G with respect to the, sorry, I'm looking here. Can you guys see this okay? Mark, can you see it?
It's showing up all right. It took a second for it to autofocus, but it's fine.
Okay, I'm just making sure. Okay, so the rate of change of G with respect to T is proportional to the square of G. Again, we're taking this verbal description and we're trying to write a differential equation for it. So let's see what I can do here. The rate of change of G with respect to T, that's going to be dg dt is, so equals, proportional to the square of G. So K, some constant of proportionality, times, and I can put that little dot or not, it doesn't matter, G squared, the square of G. Second example, the rate of change of H with respect to T is proportional to the square root of H. So the rate of change of H with respect to T, there's my dH dt, is, there's my equals, proportional to the square root of H. So K, and then times the square root of H. Third one, the rate of change of J with respect to T is inversely proportional to J. The rate of change of J with respect to T, that's going to be dJ dt, is, and then inversely proportional to the square of J. Inversely, oh, it's a little different. So in the other two examples, and actually in the A and the B example, we had what was pretty much a direct proportionality, even though it didn't say direct. That's implied or assumed. Here is explicitly, we're saying inversely proportional. And so for sure, I need to think about that J being in the denominator. So dJ dt is equal to K, my constant of proportionality, or my coefficient of proportionality, divided by J. All right, here's one for you to try. I'm going to read it out loud.
And I'm going to play at home.
Oh, okay, Mark. Oh, and by the way, Mark's going to reveal his answer. When I ask you guys to do it, Mark's going to reveal his answer, or vice versa. When he's doing the lead teaching, I'll be revealing my answers like I'm a student in the class. And then they may or may not be right. Okay, like we're gonna look at his answer and decide if he's right or not. Okay, so here it is. The rate of change of M with respect to T is inversely proportional to the cube of M. So the rate of change of M with respect to T is inversely proportional to the cube, the cube root. I don't know if I said that the first time.
I was listening to you too.
You were listening? Okay, well, you could have left it wrong.
It's all right. I write fast.
Uh-huh.
All right.
And I think you can switch me off, right?
Yeah, there it is. I'm actually having trouble with it right now. Oh, there we go. Can you still hear me? Because I just lost it.
I can hear you.
Okay, sorry.
Do I need to do stop?
No, no, you're fine. Zoom just got goofy.
Mm-hmm.
We're fine.
Okay, so let me read this out loud because I see now Mark's screen showing. It says the rate of change of M with respect to T, that's the dm dt, is inversely proportional. So me personally, I would have the K in the numerator, but I love the way Mark wrote this, where he has K times and then 1 divided by the cube root of M. So inversely proportional to the cube root of M. It can be written either way. Oh, he's got a little nice variety going on here. What's it? I got to move this over here so I can see.
It's over M to the 1/3.
Oh, I love that, Mark. M to the 1/3 right there. That's exactly right. All really good expressions. You don't have to say all of them, obviously, but you know, any one of those would be correct. All right. We good?
Yeah, go ahead and grab it back.
I'm going to go ahead and share. So to all you watching, what is today? Thursday? I think Thursday was.
It's Wednesday. It's Wednesday. Wednesday.
What? Today's Wednesday. Oh my God. I've been Zooming for less than a week. I feel like I've been Zooming my entire life. That's how fast everything has happened. Okay. I'm still not an expert at it whatsoever, but with more practice, obviously you get better. All right. Here's our number 5. Number 5 says the rate of change of a population of bees and then lowercase b over time is proportional to the population of bees. So the rate of change of a population of bees, B, so there's your dB dt, is, that's my equal sign, proportional to the population of bees. So that would be K and then times B, the population of bees. Can just even be KB. You don't need to have that showing, or sometimes you have parentheses around, especially a base that might be something like a 1.4, or something like that. Okay. 6 is one for you to try on your own. I'm going to try and read it out loud correctly this time. It says the rate of growth of a population of zombies Z over time is proportional to the population of zombies. Mark's going to show us his result this time.
Yep.
Again, whenever I'm going to wait just another 30 seconds, Mark. The rate of growth of a population of zombies Z over time is proportional to the population of zombies. You want to boot me off? Do you know?
Sure.
Okay. Okay. Ah.
Yeah, I was much better prepared that time.
Okay. Huh. How do we feel about this one? Let's take a look. dz dt, that's the rate of growth of a population of zombies, Z over time, that's dz dt is equals, and then proportional to the population of zombies. So K times Z. I like it.
Yay.
And this is Z's. Yeah. Why would we cross our Z's?
Because my 2's look like that.
Yeah.
Not quite that bad, but close enough.
Exactly. All right. We're going to try 13, which might seem kind of weird, but
Remember to grab it back.
Yeah, I gotta reshare mine. I'm going to do that. But this document has 22 examples, which is great. You can go back and look at all 22 examples, and we have the answers for you as well. But that's great for a class because a lot of classes have about 22 students. Miss Vicki Carter's class probably does. That's why she wrote 22 of these. But I'm just skipping to 13. So in this one, it says, in a community of F farmers, the number X of farmers who own a certain combine changes with respect to time T at a rate that is jointly proportional to the number of farmers who own the combine and to the number of farmers who do not own the combine.
What is jointly?
Say it again, Mark.
So what is jointly?
What is jointly? Right. Well, what is with all these words? My gosh, these went from really easy problems where people were probably thinking like, this is too easy, it's going to get harder. And now all of a sudden it is. Okay, so what is jointly? Jointly means that there's going to be 2 different variables there on the right-hand side interacting with each other. If you don't see the word inverse, it means they're interacting by multiplying. But if you see inverse, then one of them is going to be in the denominator, or maybe both, But let's go back and read this again. There's a lot going on in this problem that we have to pick apart. It says, in a community of F farmers, the number X of farmers who own a certain combine changes with respect to time T at a rate that is jointly okay, I think I see my differential expression right here. The number X of farmers who own a certain combine changes with respect to time T. That right there is dx dt. I'm going to go ahead and write it right here. So that right there is dx dt. The number X of farmers who own a certain combine changes with respect to time T. And this is happening at a rate that is jointly proportional to the number of farmers who own the combine. The number of farmers who own the combine. Okay, the number of farmers who own the combine, that's X. To the number of farmers who do not own the combine. The number of farmers who do not own the combine is not F. So the number of farmers who do not own the combine is actually F, the total number of farmers, minus X, the number of farmers that do own the combine. Because you either own the combine or you don't. There's nothing in between. So total set F. All right, so dx dt is equal to K, and then times X, and then times, in parentheses, F minus X. Here's one for you to do on your own. It is not as hard as that farmer problem. Well, it's not as long anyway, but also not as hard. This one says the rate of change in the height h of a tree with respect to its age a is inversely proportional to the tree's height.
Excuse me.
And you know what, Mark, I'm going to stop share because I think you're
Okay.
going to share this one with us, right?
Yeah, you want me to just
So-
go ahead and put mine in, or do you want to give
Yeah, no,
everyone a
you
few-
can put it in. Yep.
All right. Here it comes.
Okay. So let's go ahead and read the verbal description out loud and also look at the differential equation that Mark wrote. So it says here the rate of change in the height h of a tree with respect to its age a so the rate of change of a height in the height h of a tree with respect to its age a, I see a mistake right off the bat. Yeah. So it should be DHDA instead of DHDT. Yep.
It's really easy to put that DT reflexively.
Yeah, especially if you are doing a lot of related rates. Okay, good. Thank you for making that mistake, Mark. Is equal to is inversely proportional to the tree's height. So equals K divided by H. There's that inversely proportional. The H has to be in the denominator. Nice. Okay. There's going to be another one for you to do on your own. So I'm going to go ahead and change back to my document camera now. And read that one out loud to you. Since.
Yep, you got it.
Yeah.
You reading it, Verge?
Yeah, I was letting them read it, but I'm going to read it.
Oh, I'm sorry.
Read it. That's okay.
I'm the kid in the back that wasn't listening.
Yeah. Suppose a virus is spreading in a network of computers. There are M computers in the network. The rate of change of the number of infected computers is jointly proportional to the number of computers already infected, J, and the number of computers not yet infected. So suppose a virus is spreading in a network of computers. I'm going to give you guys another 30 seconds to do this. Mark, did you do this one?
Yeah, I did.
Okay.
I feel okay about it, but I'm becoming very self-conscious with the size of the projection that my J's are very shady.
Your J's are shady?
Yeah, I'm going to work on my J's. I'm not happy with that. It's an elongated semicolon. All right. Anyway.
Yeah, J doesn't come up very much in calculus, but of course there's the I and J vectors, right?
Right. I think I'm going to use the vector J next time. But
yeah, it's interesting. Like we've been working on this for about a week, and I'm talking to teachers now, not really students, but it's interesting the little things that pop up that that aren't really part of your classroom teaching. So that's exactly. All right. So let's see. Let's translate this. Suppose a virus is spreading.
I was taking the notes as you were writing. So
Suppose there are M computers in the network. The rate of change in the number of infected computers is jointly proportional to the number of computers already infected, J. So the computers that are infected are definitely J. So J is the infected computer. So DJ dt. And the number of computers not yet infected. So the not yet, this is a lot like the farmer problem. So you want to find that difference M minus J is not yet infected. Total number of computers is M, and then they are jointly proportional. So they're getting multiplied together. 100, Mark. Good job.
Yay.
All right. I love this next one. One thing that we worked on a lot this year at my school in terms of faculty is talking about relevance. And, what are you teaching? Is it relevant? And so as we were doing this example, Mark and I, we thought that it was a really interesting example because it really is a law, and we looked it up. So we're going to talk about what this law is in just a little bit, but we'll translate it first. The rate of change of a level of response R with respect to the level of a stimulus S, so here's my variables R and S, is a joint proportionality between the level of the response and the inverse of the level of the stimulus. This differential equation, see, it's abbreviated DE. This differential equation is known as the Brentano-Stevens law. So let's go ahead and translate it, and then we'll kind of talk about that Brentano-Stevens law, just anecdotally, just because we're kind of interested. So the rate of change of the level of response R with respect to the level of a stimulus S, that is going to be dr ds is equal to a joint proportionality between the level of the response. So the level of the response is R, so perhaps KR divided by, and then the inverse of the level of the stimulus divided by S. So that differential equation describes that entire situation. So go ahead, Mark. You were the one who guessed it correctly. What is the Brentano-Stevens law? Like, just tell us what field it's in.
It's psychology.
It's psychology, right? So, it's just interesting to me because a lot of times what we do in calculus is, of course, related to physics, a little bit chemistry, maybe a tiny little bit biology, but here we are looking at it from a psychology perspective. We're going to do one or two more. This one I'll do with you, and then we'll do another one where you'll kind of do it on your own, and then we'll wrap up. So we're getting close to the end of the lesson. So number 17 here, this is one I'm going to go ahead and translate and do with you guys. It says for the first 9 months of life, the average weight W in pounds of a certain breed of dog increases at a rate that is inversely proportional to time T in months. So for the first 9 months of life, the average weight W in pounds of a certain breed of dog increases at a rate that is inversely proportional to time T in months. There's a lot hiding here. Like, it's kind of hard to figure out exactly what's going on. But in this beginning part up here, I'm interpreting this as dW dt, how the weight is changing with respect to time. And then this is equal to K divided by T. It's inversely proportional to time T in months. One thing that's interesting about this differential equation, in addition to many differential equations, is that there are restrictions on the domain going on here. We can talk about those restrictions. Mark brought this up yesterday when we were going over this lesson. And what I mean by that is the domain.
Do you mind if I steal your screen?
Yeah, steal it. Go for it. Yes.
So we just talked about the domain restriction. They had said in the first 9 months, so that's why I chose this 0 to 9 interval. And then with this T in the denominator, T can't be 0, so I dropped that 0 out of the domain.
Good. And a lot of times differential equations describe a situation over a certain period of time. It's only true for this particular time interval or for this particular, interval, and then something else happens. Maybe it's some sort of a piecewise function or whatever. So a lot of times we will want to talk about those restrictions on the domain, and this is a good one to bring that up for.
And don't be too nervous about this. Typically, if you're going to be expected to show that domain, it's going to be a situation where they're going to explicitly state any domain restrictions. So it's not something you have to think about all the time, but this one did mention that time period, so that's why I put it in.
Yeah, good. Okay, the next one is going to be one for you to try, and I'll read it out loud as well. All right, so this is number 18, and it says the height h in feet of a certain tree increases at a rate that is inversely proportional to time t in years. The height h in feet of a certain tree increases at a rate that is inversely proportional to time t in years. Okay, Mark, you want to show yours?
There we go.
The height h in feet of a certain tree increases at a rate that is inversely proportional to time t in years. Yes, that's exactly right. It's not as clear cut as the ones from the beginning, but the dH/dt is implied in the English phrasing that's given in that problem, and then is equal to k divided by t. And again, it could be c divided by t or any sort of constant there. Anything else you want to say about that one, Mark?
No, I don't think so. I think
Okay.
you are doing a fabulous job.
Wait until they see the next lesson, which we haven't practiced 3 times, right?
That's all right. the content gets. Yeah. We're going to get to play with these. That part will overshow anything else in the next couple of days.
All right, let me go ahead and share this last one here. And this one says, number 20, barometric pressure P measured in millibars changes with respect to altitude A measured in feet above sea level at a rate that is directly proportional to the altitude. Barometric pressure P measured in millibars changes with respect to altitude A. Ah, how nice. At the very end here, we have a very explicit dP dA. dP, change in the barometric pressure, divided by dA, change in altitude, is equal to, this rate is directly proportional to the altitude. So we can write CA if we want, or we can write KA or anything like that. So again, there were 22 of these and we didn't do all of them. So tomorrow or whenever you next watch the video, we will start by sharing one of the other ones that we did not yet do. That'll give you a chance to go through and practice. But we'll go ahead and start by doing one of the ones that we did not do, go over that, and then we'll do our next lesson. In addition, just in terms of, I know what's happening for our third lesson, some of these lend themselves very nicely to slope fields. And so we might pick one of these for one of our slope fields as well. So remember, and Mark, you might go ahead and share the PowerPoint right now.
Absolutely.
The end of our PowerPoint. Remember that you can go to the description in the bottom below each video, and you can see the the little link that you can click on, and there's nothing in any of those folders right now, but each day we will be adding things to the folder so that you can either download the materials before you watch if you're not watching it live, or you can download the materials after you've watched it live and kind of go back over the material and also get ready for the next lesson. Our next lesson is going to be 7.2, and it's going to be verifying solutions to differential equations. Hey, Mark, I think I've got a gray screen.
Oh, sorry.
That's okay. Mark,
Did he come back?
He's always
I'll tell
doing a whole bunch of stuff.
I will tell you. No, I will tell you exactly what that was. That was the file going into the Dropbox.
Oh yeah, that's awesome.
So,
but this QR code here, you can even, all the modern phones, you can hold up your phone to it. It'll take a picture of that. But in any case, we are so grateful for this opportunity. We hope that we're helpful to you. We hope that if we make mistakes, that somebody tells us. We have a lot of very, very smart friends, and they will email us, I'm sure, right away if we make a mistake. We will fix it for you during the next lesson, and we will just keep moving forward one day at a time. We're very grateful again, and really thinking about all of the students, just kind of all by yourselves. It's very hard to be a teenager and be alone like this with the adults in your husband as your only company. I know, I have a teenager. It's been challenging, but I think you guys can make the best of the situation.
and I just want to add, I know we have a bunch of, like you said, there's a bunch of people that will correct our mistakes, but we've also got a bunch of people that have been texting me during this, and the Dropbox is confirmed, so that file is up there for you guys. So got a little bit of homework. Do what you can. This stuff is, as you saw, it was easy today, and we're going to get to play with these equations the next 2 days. I'm really looking forward to that part.
Me too, and I hope you join us next time.